The algorithmic probability of an object takes into account all the programs that calculate x, not just the most concise one. The program size complexity of x is the size in bits of the smallest program that makes u calculate x. That's h sub u of x. But p sub u of x looks at all the programs that make u calculate x, and it sums their probability of all these programs.
X is a bit string.
X is any digital object, and actually I would use Lisp. Lisp is sort of like using their symbolic expressions. It's sort of like using Zermelo-Fraenkel set theory and finite sets. So that's technically how I do it. Lisp is a very powerful, very simple, elegant language. Well, I have my own versions of it for mathematical purposes, which is like set theory with finite sets. So instead of a set has several elements, right, in no particular order, and you write it like this. Lisp is lists. A list has a first element, a second element, a third element. You use parentheses rather than curly braces. You don't separate the elements by commas. You leave blanks. And you can nest lists. So you can have lists whose elements are lists, whose elements are lists. So you can build arbitrarily complicated structures, and they basically are like algebraic expressions, sort of like a generalized kind of algebraic expression. Also, you can think of them as trees, but they're these big composite objects. It's like set theory with finite sets. And you can have sets of sets, you can have lists of lists. And in set theory, you start with the empty set, and you build everything out of that with set formation. But in Lisp, you're allowed to start with words and numbers. You have atoms and build sets out of them. So you have a lot of, you're given more things that are not lists. Whereas in set theory, everything is a set. You build everything out of the empty set. You build all the numbers out of the empty set. That's a von Neumann's construction. Well, anyway, so there are nice formalisms for doing this, and in my books I go through this explicitly in a number of my books, if you want to see what I think is the best formalism for actually doing all of this and programming all of this. Okay, but anyway, a key point is, the same way that your universal machines that you use in this theory give you the most concise programs, to the extent that that's possible, they give you the highest possible algorithmic probabilities. The algorithmic probability of an object, a digital object, is the probability that a monkey typing on the keyboard will type in a program that calculates that object. And you minimizing the size of the program to calculate x means that you're maximizing the probability that a program typed at random will calculate x. So in this precise sense. So these universal Turing machines that are used in this theory give you small programs, and they give you high probabilities. And the connection between the size and bits of the smallest program for x, so pick a particular u, and let's keep it fixed with the properties that I said, universal machine, but that's like picking your language for describing objects algorithmically. Here, this is the size and bits of the smallest program to calculate x, and the first important theorem about all of this, which is in my 1975 Journal of the Bayesian paper, by the way, let me advertise, is so it was a thrill discovering this. I still remember. It was at the same time that I was calling Gödel on the phone, actually. It was an exciting period in my life. It turns out that if you take the minus log 2 of if the probability of calculating x with a program picked at random is 1 over 2 to the k, there in fact will be a k-bit program that calculates it. So this is a result saying that if you have a lot of long programs to calculate x, then there must be a concise program to calculate x. If you have 2 to the k n-bit programs to calculate an object, then there has to be an n minus k bit program to calculate that object. In other words, the most concise program for an object is essentially unique as a consequence of this result. So this is a very important result, and if you remove this, it's sort of a definition in Shannon information theory. My intention was to get out Shannon information theory with a reinterpretation. Instead of an ensemble notion of information, this is a notion of information that applies to individual objects. You know, it's a different.
Also, that formula is very appealing for statistical mechanics, because it's a kind of relation between partition function and the free energy.
Is that? this would be the energy, or am I? No, it's the other way. I don't know.
It's like a Boltzmann wave.
Yeah, yeah. Well, Boltzmann statistical mechanics have to do with probabilities, right?
When you sum with all possible x, you get the partition function.
Yeah, the entropy is really log of a probability, right? Isn't it? Something like that. Right. So this is also a familiar formula in statistical mechanics. Sort of. Okay, the next major theorem that I'm very proud of, because this no one else got, because a lot of this work was independently done by different people. I've mentioned the main names already, but as far as I know, nobody has claimed to have gotten this result of my journal of the UCM paper. This is a joint complexity, the size of the smallest program to calculate x and y. This is the size of the smallest program to calculate x, and this is the size of the smallest program to calculate y if you're given x for free. And what this result says is that if you get the smallest program to calculate this and the smallest program to calculate this and this, that essentially is the same as the size of the smallest program to calculate the two together. This is, again, an identity in channel information theory if you remove this. And to get this to work, you need two ideas, not just the self-delimiting programs. You need to define this relative complexity or relative entropy in a way that is a little more subtle than the usual way. You're not given x directly. You're given more than that. You're given a minimum size program for x. And then this relationship works perfectly. That this is bigger than this is sort of obvious, because one way to calculate the two objects is to start with a program to calculate one and then add to it a program that calculates the second one from the first one. But so that this is greater than or equal to this is trivial. But it's the other direction that it's not trivial. The other direction is telling you that if you have a program to calculate two objects, you can subtract from that the size in bits to calculate one of them and get a program to calculate the other one from that one. So that one is much more subtle. Okay? So anyway, but this result, beautiful as it is not that relevant to, this is important in algorithmic information theory, but it's off for metabiology. And the reason is that this is essentially what I refer to as mutation distance. This is the size of the bits of the smallest program to get, if you think of this as an organism, from this organism, this is the mutation distance, and 2 to the minus this would be the probability of a mutation that takes x into y. This is the smallest mutation, the simplest mutation, the most probable mutation that gives you y from x. You see? So this is so it's a very basic thing in metabiology, because it has to do with what a mutation is and what the probability of a mutation is. But there it's not appropriate to have this be the most concise program to calculate x. You see, because, as I said, organisms are not elegant programs. Organisms are programs in my model, but they're not the most precise program that calculates what they calculate. So you don't have, you have a slightly less elegant, from the point of view of algorithmic information theory, notion of relative complexity or relative entropy. But that's the appropriate concept for the other field. But you lose this, but all the rest works fine. So all the rest of algorithmic information works fine. You just lose this particular result. Well, you lose it in one direction. You still have this being greater than or equal to this, of course. So that's a key technical issue. Now, this business here is really important. Some people, I like to call this algorithmic probabilities. You know, this is the chance that a monkey typing on a keyboard will give you a program that will make you calculate x. Some people call this the a priori probability, which is also a good name. I never use that when I write about it. But the idea is, this is a very natural probability measure on all objects. It's the size. Well, through this relationship, it's 2 to the minus the size and bits of the most concise theory for x. It's the probability that a algorithm will give you x as output. And the point is, these are maximal. So essentially, there is, if you change the universal computer or the programming language you're using, these probabilities will change a little, but not too much. You're essentially getting a maximal algorithmic probability. And so what that means is that this is sort of a natural measure. That's why people think that this is the right definition, because so in other words, algorithmic information theory believes that they have the right notion of how to associate probabilities with algorithms, because you're doing this in a way that gives you the biggest possible probabilities. It gives you the most concise programs, the most expressive programs, and it gives you the biggest probabilities. Okay, so this is why the halting probability omega is believed to be a sort of a natural mathematical concept with surprising properties, and this is why doing a concept migration from this field to metabiology, this is why I believe this is a natural way to define a mutation and its probability. Okay, so this is the whole point. Okay.